I told you right from the beginning that you have 4 week sessions to deal with the topics that we are supposed to deal with. So when you come in with which unit are you teaching, which unit are you teaching, you run into trouble. Get your topic and move along with your topics. That is the best way I can suggest to you. There are other programs which are not run like your design or your model. So we cannot use the unit concept. For unit, usually it's in 6 units. And the same thing has been moved to the switch here. But we are doing that in 4 weeks. So I don't want to be trapped, and I don't want you to put that in your head about unit. I rather wish you deal with topic. That should help you and guide you. So I hope it works for you. So like I was saying, we have this line I have shown here for us to deal with. This line. And I asked every one of us, we are currently online, we are around 94, that measure this length, the length of this line, and then write it on a paper. So whether you are using a ruler or you are using a tape, whatever means that you have to measure, you will measure and record. After recording on the paper, I'll ask you to fold the paper and give it to me. So we create something like a box and put all the measurements in them. And then I will thank you all, and then you return to your base. Now, when I go to open that box and I begin to write your measurement on the board, the first thing that will be clear is that for all the 94, now 97 people who are online now, if they should submit their results, I will not get one value representing the length of this line. So if I'm not getting one value which is representing the length of this line, why is the case so? And whose measurement are you going to call the correct one? So for the simple fact that out of the 94, 95, or 97 people who attempted to measure the line I've shown or I'm sharing with you, and after your activity, I pick your paper and write the scores or the value on the board, and I don't get one value to represent, or I don't get the same value across all the 97, then there's a problem. Now, once you don't get one value, it means nobody has the true value. Because I cannot take one measurement as the standard and consider others wrong. And the reason why all of these things become necessary for our understanding is that the way we may even pull our tape, one person to the next and to the other, is different. The kind of tension we apply in our tape is different. The kind of alignment we will do against the object we are measuring differs from one person to the other. There may even be technological approaches that may be different. What about your eye that is watching the tape or whatever measurement to pick the value? We all dress nicely and we go about, we can see. But I tell you, scientifically, we don't have the same power of lens in our eyes. Some see well, others don't see well. But we may all look nice and appear nice in our day-to-day running. So when the person is being challenged in levels like that, including, let's say, the power of the lens of the eye, that person is not going to be able, because he doesn't even have the ability to measure whether the power of the lens of his or her eye is below standard or is weak or requires some adjustment. He will call out whatever he read based upon his ability to read. So in the end, once you don't get one value out of the 97 people who attempted the measurement, then whose measurement is right and whose own is wrong? And clearly that shows that nobody knows the exact value of the line I've drawn. Whatever we do, whether we measure 100 times, 200 times, if we are trying to estimate that true value. We are trying to come up with a measurement that is close to that true value. But the fact is that we still don't know the true value. And that is the concept of the theory of measurement. So we say measurements are never exact and will always contain errors. Who then is error? Error is the discrepancy or the difference between your observed value you've written and the true value which we do not know. Take note of the definition again. Error is the discrepancy or difference between your observed value or your measurement, what you call your measurement, and the true value that nobody knows. What is the interpretation? All measurements you measure or you carry out or you record, whether in the food book, whether in your jotter or whatever, that value you have recorded is not a true value of the measurement. So that value you have recorded contains error. As simple as that. Because whatever you call your observation, when I measured the rope, I got 4.3. And somebody will say, I got 4.4, I got 4.1. All those things, they are good. That is your estimate of the true value. But nobody knows the true value. So in the end, whatever that we capture as our measurement will contain error. Ima, you have your hand up.
Yes, I just want to get more understand. I think that accounts for the reason why when we're doing construction in mathematics, there's always that allowance of 0 point plus 0.1 and then minus 0.1, and all of these answers are deemed correct. Am I
Fine.
right?
Yes.
Because of
Yeah, right.
error. Uh-huh. Okay.
We call
Thank you.
it allowance that we give to you. The allowance because we understand and appreciate that every measurement has error. But we must also work within a certain framework or threshold. So what we give to you is what we call allowance. So that within that you make a judgment of fairness to a particular measurement that has been obtained. So that is it.
That's
In some parlance, they will call it the accuracy of your work. So they will give a certain value, plus or minus. The idea of the plus or minus is to give you a range for which when you fall within, you are satisfied that you have done a good work. But it's basically because there are errors. But there are some that are beyond acceptable limits. So the bracket or the defined range tells you to be cautious and make sure you are within. Than that, when your work reveals a position outside that range, it is rejected. All right. So every measurement has errors. Why? The true measurement of any measurement we conduct is never known. And whatever that we call our measurements are best estimators of the true value. But it doesn't still make it correct as the true value. So that is it. So error is always a difference between your measurement and the true value, which we do not know. But we can have an idea whether we are doing a good job or not. And that will come up later. We call that one accuracy. And then there's another one called precision. So that is it. So when you have questions or you see past questions that is talking about you explaining the theories of measurement and error, then basically what we are saying is that surveying undertakes a lot of measurement. But the measurement that we take contains error because no measurement is exact and the true value of any measurement is never known. So every measurement you take has error. Error, again, I said, is the difference between your measurement values and the true value which you do not know. So these are the things that we expect. I've seen in script I've marked, and I'm saying it again because you are the group. I spent a whole 1 week weekend lecture speaking for more than 2 hours about your attitude, your preparedness, and the things you have to be cautioned about. Some have suffered for it. I hope you don't suffer for that. So when we tell you to state and explain the concept of errors, and you begin talking about types of errors, you have deviated. I'll mark you 0. What I've explained here, I've not mentioned types of error and sources of error in this. I'm just telling you the fundamental truth, which is that every measurement you take has error because the true value of any measurement is never known. Therefore, all measurements have errors. Simple as that. Do you have any problem with what I've explained to you on the theory of measurement and errors? Good. So on the slide, you see measurements are never exact and will always contain errors. Any measurement includes error because the true value of any measurement is never known. The closest that can be found is the best estimator of the measured quantity. That is your data. What you record and you say this is the length of the line. That's your data. So that is what we call the best estimator. It doesn't still equate to the true measurement. And at times it does not even show that you did a good measurement. But to you, that was your best estimator. That is it. An error in a measurement, therefore, is the difference between the measured value, or what we are calling observation, and then the true value. So what are the highlights? No measurement is exact. Every measurement contains errors. The true value of a measurement is never known. The exact errors present is always also unknown. Because we said error is the difference between your measurement and the true. And since you don't know the truth, we cannot quantify exactly how much error is in your work. It still does not mean that hell has broken loose, so survey should stop and we cannot do measurement. We can still do measurement. There are other models we adapt to check our work and to determine whether we are doing a good work or not. One of them is what our brother raised, what we call accuracy. So we will look at all those things very soon. It brings us to the types of errors. And here again, types of errors is not equal to sources of error. If the question is talking about types of error, and you go and write sources of error as your response, you will get 0. So you listen and you listen carefully. This is talking about general errors, how they present themselves. Sources of error is looking at who is causing that type of error. So we are trying to trace in sources of error who may have probably brought that error into the measurement. But this type of error, which is called types of error, is basically a general form of error. It's surveying. There are 3 forms. We have mistakes. We have systematic errors. We have accidental errors. These are the general forms of error in surveying. This is not sources of errors. Surveying. So when we talk of mistakes, how do we mean or what are we looking at? Mistakes is what we call gross error. In some literature, they are also called blunders. BLUNDERS. There are errors that come about because we were not careful. The one who was conducting the measurement is not careful. So he ends up not getting focused with the work. Inexperience can also be an issue, especially where the kind of measurement requires very high skilled application. and then you go and give the work to somebody who has just joined, a novice of a sort, doesn't have any years of experience of conducting that measurement, then out of the blue, boom, you ask the person to go and do that measurement. The person can introduce mistakes into the activity. So that is their nature. That is their nature. It may also result from carelessness and poor judgment or confusion in the mind of the observer. So these are the characteristics of mistakes: inattention, inexperience, carelessness, and poor judgment or confusion in the mind. But the one taking the measurement is the one who causes this kind of error. If a mistake is undetected, it produces a serious effect on the final results. For instance, you measure the length of a rope. You measure the length of a rope. And after measuring, instead of writing exactly the answer straight or your measurement straight, somebody engage you in a conversation. So out of inexperience, out of inattention, out of carelessness, you weren't listening to the person. It could be that you're in the field, and whilst you did the measurement you're going to write, a friend calls you on your phone. You were not focusing on the work. You decided to listen to the call. Then when you finish, somehow you were struggling to remember the measurement you have done. So something that you measured that was, for instance, 13, you ended up writing 30 instead of 13. Or a measurement that was supposed to be 16, you ended up writing it as 19 because of carelessness. Usually, if all these characteristics, you avoid them: inattention, inexperience, carelessness, poor judgment, you won't have mistakes in your work. Mistakes as a kind of error will never pop up in your work. Anytime you see a mistake arising for a particular work, then these characteristics were in the midst of the work: inattention, inexperience, carelessness, and poor judgment. Other than that, you will hardly have mistakes as part of the errors that are likely to influence your final outcome. So not happy. But of course, if you give room to some of these things, then you can have mistakes also coming to your way. How do we avoid mistakes? At times, you run some independent checks. For instance, if you have a building to deal with, the building is a rectangle. So let me put this one here. One, sorry. Two, you have this. And then you go this way. I'm just trying to get something like a rectangle. All right. Now, if the drawing was correct and I got it right, this side, if it's a rectangle, will be parallel to that side. And this side will also be okay to this. Now, what we call in the independent check is that if I'm dealing with a rectangle, I don't need to measure all the four sides. I can measure this side here, the long side, measure this short side, and then do what we call a plus measurement. Plus measurement is you record a third entity that will serve as a check. So when I record this one, I'll put it as a plus measurement on the side here. And then later on, compare with what I had when I did the measurement here. It should be very close or exactly the same. So once the two are the same, I am assured that the one here will also be equal to the one there. So I have closed the measurement and I have gotten the four-sided figure measured correctly. But my actions show that I measured two. I use this one and I use that one. Why? Because I believe the corner here can be right angle 90 degrees, or it can have an angle which will be opposite to this other one to give us the four-sided figure or rectangle. So that is with that. So I measured two measurements, which is typically this side and then that side. Then I'll add this third one, which I call my independent check, to see if this measurement is close to this one. While you are doing this in the field, you are likely never to encounter mistakes or gross errors or blunders. So that is with the mistakes. Then we go to the second one, systematic error. And we say that this kind of error is difficult to detect. It's difficult to detect. You cannot easily determine systematic errors, but they have a form and nature that they appear, which mathematically you can. So it's a systematic error. Systematic means it builds up gradually and in a consistent manner. It builds up gradually in a consistent manner. And as long as you keep doing the same thing, or what we call the same condition, you keep having the same sign and size. I always use this simple rudimentary exercise to explain. You have a measuring tape to measure a length, and then somehow, either through inattention or not focusing on work or carelessness or whatever, the tape breaks into two. And then because you have no means of using another tape on the field, you took the two ends and then tie it into a knot so that you can still use the tape for measurement. As long as you use the tape and crossing or passing over where you tie the knot, there will be consistent and there will be systematic error in your measurement. What do I mean? You have a tape that was this long, and then the tape got broken here, or it got torn or whatever. So now from that one piece, you have two pieces, this side and then this side. Then you don't have any tool in the field, so you decided to tie a knot around here. So you held a bit of this, you held a bit of that, you created a knot, you tie it. Now, as soon as you did this tie, you've been able to fix the torn apart end, but you have influenced the dimension of the tape. So if you have a measurement of this nature to measure, if you have this measurement to measure, and you come and put this end of the tape here, and you stretch it, the knot is going to fly around this end. But in the end, your tape was able to reach this end, and you read your value. The value that you read on the tape is going to be influenced and affected by the systematic error of this knot. So if the knot, for instance, took 0.5, it shortened the tape by 0.5 over that stretch. This is going to affect your readings that you pick as your measurement. And that's what I mean by the systematic error. So as long as you use the tape, if you use the tape for different measurements 10 times, and all of them, you were pulling the tape from one end here to the other, and the knot was in the middle. From one end here to the other, and the knot was in the middle. You will consistently be incurring that systematic error of 0.5 in your measurement. And that's why we call it systematic error. How do I deal with that mathematically? What you do is later on, this tape can be stretched against a standardized length. What we mean by standardized length is that you can have some two pillars on the ground, which are a certain distance, fixed and known. Then you go and stretch the tape over those two pillars. See the reading on your tape, and then check with the other readings between these two pillars of the measurement. It will give you an idea of the error involved. And you can use that one to correct all measurements you did with that side of the tape. So that is the nature of systematic error. It has a definite way of affecting the data. And as long as you keep doing it, that same condition, that same effect will be repeated in your measurement. So how do I fix it? Having measured between two poles with a certain standardized distance and compare with what your tape gives you, you can use a proportionality effect to reduce the effect of systematic error in your measurement. So that is how we correct for systematic error. And that is why the note is talking about the fact that you can use some definite mathematics or physical law or a correction can be used and applied to your measurement to take off the effect of a systematic error. The third is called random or accidental error. The third is called random or accidental error. This is the most difficult part of the three types of errors in surveying that we want to avoid. Like I said, for mistakes, if you are careful, you will not get mistakes as errors in your work. If you are experienced, you will not get mistakes or blunders in your work. Systematic error. If I know or I'm aware that the machine I'm using has a defect, I need to check it against standard measurement to evaluate the level of the defect. Then when I use a machine or instrument for measurement, I correct my scores. I correct my measurement values with mathematical models that will support that correction. So that in the end, I'm taking systematic error out of the picture. So that is with it. But with accidental, even tracing the source of the error is so difficult. Like I was saying, you are trying to read from the tape using your eye, and the power in your eye, the length of your eye, is getting low or it's getting weak. You, the one taking the measurement, will be difficult for you to tell. So you assume that your measurement is okay. That can lead to random errors. That can lead to accidental errors. So in surveying, actually, our practice and ethics and all that we do when you're in surveying is try to avoid accidental, trying to avoid mistakes and systematic error. That one you can manage. That one you can do something about. But accidental error, you cannot eliminate them completely. It is the same reason why our brother was saying that you do measurement and you are giving plus or minus 1. Because the concept well understood and being applied, you can avoid or eliminate mistakes and systematic error, but you cannot take away accidental error. You can minimize their effect, but you cannot exclude them entirely from your measurement. They will always be associated with your measurement. So they tend sometimes in one direction and at other times in another direction. They are equally likely to make the same apparent results too large or too small, depending on where the weight of the impact is. Are we clear?
Yes.
Yes, sir.
Good. Now, interestingly, this accidental error or random error follow a law we call the law of probability of accidental error. They follow a certain error, a certain law of probability, chance of occurrence. In fact, in their practice, when you are doing the measurement, they tend to cancel each other. They tend to cancel each other as you are working along. So there are areas where the error will build up. There are areas where the errors will be reduced, leading to a kind of balance act. So accidental errors represent limits of precision in the determination of a value. So all that this statement is saying that, like I said, you can avoid systematic error. You can remove mistakes, and they will not be part of your measurement. But accidental, no matter what you do, no matter what, you still have them present. You can only minimize their effect. So they obey the laws of chance, and therefore must be handled according to mathematical laws of probability. The theory of errors is discussed, and we have seen that now there is a law of accidental errors that I spoke of. Investigation of observations of various types show that accidental error follows a definite law. We call the law of probability. The most important features of accidental errors, which usually occurs, are one, and this is the law of accidental errors, or the law of probability of accidental errors. Small errors tend to be more frequent than large ones. That is, they are the most probable. So usually when you do measurement, the errors that are left in the work most often are not too huge. If you were diligent, if you were careful, if you have calibrated your instrument, you can deal peacefully with mistakes and systematic error without any trace or problem. Simple as that. Positive and negative errors of the same size happen with equal frequency. That is, they are equally probable. Then the last one is saying that large errors don't occur frequently. Large errors don't occur frequently. So these are the laws of accidental errors. Small errors tend to happen more often than large ones. Large ones tend to happen less often than small ones. And then in our measurements, accidental errors tend to have positive and negative effects. And these positive and negative effects cancel each other whilst you are working or undertaking your measurements. Are we clear to this point? Because I'm moving now into sources of errors. So I've dealt with types of errors. I'm now going to sources of errors. In the case of sources of errors, we are looking at where the errors may have been generated from, or may have been caused from, or may have arisen from. But in themselves, sources of errors are traced to three things: personal, instruments and nature. So when you talk of sources of error, what are they? Personal errors, instrument, and nature. What then are personal errors? These are errors caused by the physical limitation of the observer. So here you are tracing it to who did it or who is likely to have introduced it in the work or in our measurement. So this one is directly linked to the person taking the measurement. It is not types of error. It is sources of error. Personal errors are sources. It's not types. So now what's the last statement here? And you see how I did the explanation. So that's why when you mix it up, you are wrong. You have to get it right. So personal error can be described as systematic error or accidental error. But if the question was saying sources of error, you cannot go and talk about systematic or accidental error. But when I look at sources of error and personal, the nature of the error you brought into the work can be traced to systematic or accidental. But here, my emphasis is on who is creating the error, not what is the nature of the error. Instrumental error, that's quite also simple. It is coming from the instrument you are using. Here again, the nature of the error can be ascribed to either systematic or accidental. Yet it is not the source of error. To get that technical clarification in our understanding. Source is looking or tracing where it's coming from. But the technical description there is three: personal, instrument, and natural errors. So when it's the instrument errors, it is the instrument being used for the measurement that has a defect, and the defect is transferred into our measurement. So we see instrumental errors, then the last one is natural errors. They occur from nature. You are going to do a measurement, then all of a sudden it begins to rain. But you don't want to stop. You want to finish your measurement before you leave. That rain coming down can affect the way you do your measurement. For example, if you are using a tape, which is linen or cloth, the rainwater can soak the tape. In that case, when you are pulling the tape tight to be able to measure, you will struggle because it has gotten wet by the rain, and it will now possess a heavy weight than usual. That will affect your recording. Another attribute that can come in from the natural environment is atmospheric pressure, temperature, especially if you are using one of our old friends, the chain, and temperature is too high, it can affect, but it can cause the chain to expand.
Yeah, Obo feel or lecture for 4 hours. Sure.
So that is the difference between the general types of errors: mistake, accidental stroke, random, systematic errors. And they are different from sources of error. We talk about personal error, instrumental error, and then natural errors. So note the difference and then work accordingly with that. Are there any questions or clarification being sought? Other than that, I'm moving to the next issue for discussion. So we've dealt with the theory of measurement and errors. We've seen the types of errors. We've seen the sources of errors. Can I proceed then?
Yes, Doc.
Okay.
All right, so we are now moving.
Hello, sir.
Somebody wants to ask a question. Use the hand. Okay, so I can proceed. Okay, Becca. Becca, you have your hand up.
Yes, sir. Please, the sources of error, the personal error. I was thinking that maybe it can cause the type of mistakes too. And I want clarification from that because you were saying that out of carelessness and inexperience, you can have mistakes. And I think that is a personal something because if the person is experienced, then that kind of error would not happen. Or I need more clarification about that. Thank you.
Not necessarily so. Not necessarily so. You can have a person dealing with an instrument, for instance, and not handling the instrument in the right way, leading to mistakes. The survey instrument, the other time I told you to go and read about them. We dealt with one, total station. Now, total station, for instance, when you want to use it for distance measurement, where you stand with the instrument, you must set the instrument up. You have to make sure the instrument is leveled. It's a technique in surveying. So if you go and put the instrument down and you don't level it properly, you have created a defect with the alignment of the instrument and the ground. So by virtue of that, when the instrument is doing the measurement, there will be challenges. You were the one who started it, but you imparted it through the instrument by the way you set up the instrument. So as far as the instrument and measurement is concerned, it has created or measured probably a mistake. Although I can see where you're coming from because of the kind of terms we mentioned there. But inattention is from you, but the inattention can be imparted in an instrument, in the way the instrument is aligned to do measurement. So my point here is that it is not automatic. You cannot say because we mentioned inattention, poor judgment, and it's about an individual, then mistakes are personal errors. No. Personal errors are sources of error. They can be mistakes, they can be accidental. They might even include systematic. But we are looking at who brought it into effect, not the nature of the error. I don't know if I've answered you rightly.
Yes, sir. Thank you. I asked because, after they mentioned the personal at the last sentence, they added that it can be either systematic or accidental. But I didn't see the mistake there. But you've made me understand that it can also be past. So thank you.
Okay. So can we move on? I saw a hand up.
Yes, sir.
Yes, sir.
Curtis.
Okay, sir. Sir, please, the types of error, when you are able to eliminate or do away with all the three errors, can't we get an accurate measurement?
I explained to you that in terms of the three types of error, you can avoid mistakes. You can eliminate systematic error, but you cannot eliminate totally accidental error. So what you are calling accurate is your judgment. What you are calling accurate is your judgment of the measurement. Because from the instrument to you, the human being, you are not perfect. And therefore, if you are not perfect, we cannot say human being A judgment or measurement is perfect or has no error. Not true.
Okay, sir. Thank you, sir.
Welcome. All right, so we've dealt with errors and then we have to make progress. We are going to move on and look at other aspects of activities I want to deal with. So we have looked at the types of errors and the sources of error. Now what we are going to talk about is angles and bearings. Angles and bearings. Angles and bearings. What is an angle? What is an angle? And I want to believe that as I advise you, are still picking your notes. So now we are going to talk about angles and bearings. Angles and bearings. Steven, you have your hand up.
Yes, so I wanted to contribute to what is an angle.
Okay.
And I just wanted to say that angles are formed when two lines.
You need to complete your network. When two lines do what? Steve is struggling with network.
When two lines meet.
When two lines meet. Good, good, good. Okay, Steve, you're back. Steve, you have the floor. All right. So suppose I take your general presentation or your general statement as true. I'm yet to end on whether it is true or not, but I suppose I take it as true.
I've assisted him.
Come again. All right. So I want to create a slide and then we start the discussion there.
I was saying that I have assisted him to complete it. So
Yes. Okay. So thank you. Now the statement we said was when two lines meet. Okay. So this is line 1. This is line 2. Line 1 is here. Let me use a different color. So this 1 and this is 2. When two lines meet. Okay. So by what I've done and by your definition, clearly if I'm taking what you are saying to be true, which it is anyway, then the two angles here are all possible angles, right? One I'm calling theta, one I'm calling alpha. Isn't it? Because I said when two lines meet, and that is correct.
Sure.
So how do we know whether you are talking, you are describing theta to us or you are describing alpha to us? Because the two of them have met, yes. This was the first line. This is the second line. They are all meeting here. But at the meeting point, there are two angles that are being displayed. Theta and alpha. So when I said two lines met and the angle between them is 50 degrees, how do you make a determination whether that 50 degrees is theta here or the 50 degrees is alpha there? So yes, your definition is generally true, but we need to further clear certain issues. Jackie, you have your hand up.
Sir, please, with the determination of the angle, sometimes we use the size of the angle to determine the kind of angle we are looking for. If the difference between the angles is that wide, we might consider the 50 degrees to be the alpha and then the larger number to be the beta.
Fair enough. Thank you very much. That is one approach. It doesn't always work 100%, but that's one approach. Because later on, you are going to see when we go to bearing that these lines that are meeting, for which you have done the description nicely, are also directions. And when it comes to direction, your ability to state and indicate the direction rightly is the first step in determining whether the angles you are making reference to is the correct one or the wrong one. So let's assume that at these early stages, when the two lines meet, we have angles formed. But it was saying also that the angle is not one, it's two. So it means you have to bring some clarification to the angle and to describe it. Now, if I also ask you, these two lines have met. And when they met, they are seeing two angles, theta and then alpha. These two angles, are they vertical angles or horizontal angles? Question number 2.
Hello. Hello.
Yes.
So they are vertical angles.
How did you come to that conclusion?
They are both running from the top to
I
down.
hear you. Hello.
Top to down.
Yes.
That is not a good reason.
Sir.
Jacob.
Hello.
Jacob, you have your hand up.
Sir, you can say that because, yes, you can say that because you can see that the lines continue to move upwards.
Thank you for your contribution, but I do not agree with you. Mark.
Hello.
Yeah, I think it's both. It could be either vertical or horizontal, pending at the angle that is in question over there.
Okay.
Because a straight line cannot give you an angle.
Is it Kekele Max? Kekele Max, thank you very much. Good try. I still don't agree with you. Your explanation is not clear. Oh, somebody's gone. Afifa, you were having your hand up.
Sir, because they are measured in a vertical plane.
Okay. So now you are adding something to it called vertical plane. Okay. So I will take your last bit contribution rather than the earlier ones that were given. Because when you say two lines meet, nobody spoke of the plane of consideration. So my general statement is that yes, angles are arcs between two intersecting lines. But then you find out that in the two intersecting lines, we've seen alpha, we've seen theta. So there has to be further clarification. Then again arises the issue of, is that condition describing a vertical angle or a horizontal angle? And here again, we see the distinction. Before we can call it vertical, it means that angle must be formed in a vertical plane. The confusion that most of you run into in trying to answer the question, as I saw from Max through Jacob and all the others, is that you were picturing the slide I have posed to you as a vertical plane. And that is what makes surveying technical, among other issues. Yes, the argument can be made that probably the way I've shown the slide to you is as if you're on a blackboard. But then there's also this argument that what you are seeing and you are calling the screen or the slide is actually a situation on a flat surface on the ground. Have you thought of that? Because, for instance, this is the area of reference. If I tell you that somebody has a plot, and the plot is like this, in terms of dimension, this is a plot. Somebody's plot. This is the size of the person's plot. Now, my question to you is that the angles here, and the angles here, and the angles there, and the angles there, which of them, let me call this one A, let me call this one B, call this one C, and call this one D. Which of these four angles is a vertical angle? The diagram there is somebody's plot. The angles there are in the person's plot.
Hello, sir.
So I'm coming back to you. Yes. I have maybe it's adult and up.
Sir, uh, A AB, the line AB have a vertical angle.
Please, an angle cannot be associated with a
AB.
line. An angle cannot be associated with a line.
Okay, A and B.
Okay. Thank you very much. I said someone's plot too. I hope you've not forgotten that. Okay.
Sir, is
Mark,
it a vertical?
Mark, Mark, which one is the vertical angle in there? Because your hand was up.
Yes, sir. It depends where you are standing. Any side can be vertical,
Okay.
any side can be horizontal.
Okay.
Because it can come from any angle.
Thank you, Max. Your defense is also not holding. So Sarah, Uncle.
So say, I think it's none of them because they are lying flat on the ground.
Thank
So
you
there's no way
very
you
much.
can get it.
Thank you. You have made my evening. Because I said somebody's plot, and plots do not hang vertical. How can somebody's plot be hanging vertical? A plot that you build on. It's somebody's plot. So if it's somebody's land, it's in the horizontal. So none of the angles there, A, B, C, D, can be called vertical. Yes, the slide that I'm showing to you and I'm using for the explanation, that is how I have to capture it and how to show it to you. So the plane of interest will always have to come in to clarify who is the horizontal angle and who is the vertical angle. When you take your exercise book or your jotter or your Bible, whatever it is, when you place the Bible on the table, you are in the horizontal plane. But when I go and hold the Bible against the wall, I am in the vertical plane. So depending on the plane of reference, angles can be reckoned vertical or horizontal. And when we go to bearings, this thing will come up again. Because in bearings, we are interested in the horizontal plane. All the concepts we are going to talk about in terms of bearing, direction, we relate to the horizontal plane. So angles can be reckoned in the vertical plane, for which they are called vertical angles. And then they can also be reckoned in the horizontal plane, for which they will be called horizontal angles. So always, we should be clear in our mind what is the plane of reference in the discussion before we can tell whether the angle is horizontal or vertical. Please, is that clear?
Yes, sir.
All right. So your definition is generally correct. It's the arc between two intersecting lines. Later on, those lines in surveying, we'll call them directions and still hold. So somebody will say lines from mathematics background. Somebody will also talk about direction. It's also correct. So the arc, the measurement of the arc between two intersecting directions, two intersecting lines, are all correct. But we've seen that when they meet, there are two angles. So further clarification must come. However, depending on the plane of reference, we can also talk of vertical angle and we can also talk of horizontal angle. Then in the last bit, look again at the figure that I have for which A, B, C, D is the angles we are measuring. What kind of figure are we dealing with? We have a polygon. We have a four-sided figure. In that four-sided figure, what do you think is the A, B, C, and D? Are they interior angles or they are exterior angles?
Interior.
So they are interior.
Thank you. They are interior. So you see the twist and dimension that is coming up. We saw when we have to call it vertical or horizontal, is the plane of reference. Now, irrespective of the plane of reference, whether vertical plane or horizontal plane, if it is a closed body, like a polygon, you can have angles inside the body we call interior, and you can have angles outside the body we call exterior. So you are right when you say A, B, C, D are called interior angles. Who then will be the exterior angles to this design? We'll have this one as the exterior angles to the design. One is here. 2 is there. 3 and 4. So my next question. Today I'm now pulling your legs a bit, taking you into mathematics. When we have a three-sided figure as a polygon, the name is called triangle. What is the total sum of angles inside the triangle?
$180.
180. John, you also had your hand up. Is that
Yeah,
also
yeah,
180?
180.
Okay. So the next question is,
Yes, sir, 180.
good. For the same triangle, what is the sum of the exterior angles? Say the sum of the interior is 180. Fine. What is the sum of the exterior angles? Do we anywhere recall this formula? Do we anywhere recall this formula? N minus 2 into bracket 180 degrees. Then there's another one, N plus 2 into bracket 180. Please, the 180 is multiplying the bracket output. So here is a times, but you don't write it, board math. You write it. Do you recall this expression and what they stand for? Okay.
Yes. So it stands for the
Math.
sum of the interior angles of the polygon.
Okay. Aiba, which one is for the sum and which one is for the which one is for the interior and which one is for the exterior?
The first one,
Yeah,
n minus 2
minus 2. And then
times 180 is this for the sum of the interior angles of a regular polygon.
Okay, Ata, thank you. Aiba, still about you. Aiba Jonathan. Okay, Prince, help us. All right. So Ata James is right. The one at the top here, this one, is used to evaluate for interior, the sum of interior angles. The sum of interior angles. Okay, so these are what we call the survey mathematics. Some of them borders on this. So some of the interior, INTERIOR. And the one below is for the exterior. So when it is a triangle, N is the size of the polygon. N will be equal to 3. So 3 plus 2 be 5. And 5 times 180 will give us how much? Those should have calculated.
900.
You add what? 900. Are you sure?
You said the N is what?
N is the size of the object. So if it's a triangle, it is 3.
Rectangle is 4.
Okay. So you see that when you have a triangle, there are 3 sides. So N is 3. When you put the 3 into the lower one here, the formula down here, you get the total sum of angles of the exterior, and that is 900. But when you go to the top and you put the same 3, you will get 180, defining the total sum of interior angles. So note these two formulas and what they stand for. You are still making your notes. I'll come back to it later on. So what is the idea so far? We are talking about angles. And we say it is the measurement of the arc between two intersecting lines. But we see that that does not give us a convincing answer, because when two lines meet, there are two angles formed. Which one are we referring to? So that's the question we have to find a way of answering. Now, these angles that we've mentioned, depending on the plane of reference, they can be called vertical angle if you are using a vertical plane, or horizontal angle if you are dealing with a horizontal plane. Where these angles are formed by closed objects like polygons, we can also have another characteristic of angle called interior angles and then exterior angles. This one is independent or does not rely on whether you are using a vertical plane or a horizontal plane. The rule that is controlling the issue is that a polygon or a closed object will have an inside part and an outside part. So when the angles being referenced are inside the object, they give us the interior angles. When they are outside the object, they are called the exterior angles. We've also seen that there is a mathematical relationship when it comes to the sum of the interior angles versus when it comes to the sum of the exterior angles. When we are dealing with the interior angles, our formula is n minus 2 multiplied by 180, where n is the sizes involved in the polygon. So for a triangle, it is 3 sides. For a rectangle, n will be equal to 4. So far, so good, I want to believe, right?
Yes, sir.
Good. So let me share a piece of a document with you that has this. Then I'm going to drop a PDF at the reps page that we can add just for the sake of literature reading on angles and bearings. But so far, we've seen what an angle is. We've seen types of angles. I may not have exhausted all the types, but I just spoke of two of a kind when you are looking at the vertical plane versus horizontal plane. Then I've also looked at when it's a polygon, you have the inside, you have the outside. They are all angles. Good. So make progress. Are you with me? Can I continue?
Yes, sir.
All right. Now, I'm taking you to a concept called angle of elevation and angle of depression. This analysis is interested in the vertical plane. This analysis is well situated within the vertical plane dynamics, not the horizontal plane. So what then is the angle of elevation and the angle of depression? To help our course and the discussion, I'm sharing a piece of material that has the descriptions that I'm giving out, so that specifically we know how to handle and deal with the various situations. Max, you have your hand up.
So, please, your introduction, the network wasn't good, so if you can repeat the introduction on the angle of elevation between
Hey, Max.
so,
Introduction of which one?
the angle,
Hey, helpful.
elevation, and then the depression. It was baffling the
Okay.
matter.
Yeah, if it's about the angle of elevation and angle of depression, fine. But I thought you were going to say that from the beginning. Down there, we couldn't have gone back. Thank you. All right. So, like I said, I'm just quickly sharing these documents with you. And then we look at the vertical versus horizontal issue. And then we take the rest from there. So let me share with you the document. All right, so we've seen the definition of angles as the arc between two intersecting directions. And then in the diagram, we've seen clearly the A, alpha, and then the beta. So these are all possible when it comes to angles and the two lines meeting. So we went to types of measurements and we considered the vertical plane and the horizontal plane. But I left out this one, what is called an included angle or a deflection angle. An included angle or a deflection angle. That one is here. So write it down. In my next lesson, you're going to tell me what they are. So we spoke of horizontal angles, and then we spoke of vertical angles. Then there's a special consideration under the vertical angles called the angle of elevation and then the angle of depression. So what then is the angle of elevation? When you are in the vertical plane, and you watch directly across your view, horizontally into space, you will get an angle of elevation when you attempt to raise your eye above that horizontal line to an object above that reference. So, using this diagram as an illustration, this whole block here is the vertical plane. We have an individual standing on the level and watching horizontally. When you're watching horizontally, it is the middle line. But there's an object up and there's an object down. From this horizontal view or level line view, when you raise your eye up to this object, you are defining an angle of elevation as this. Let me call that angle theta. However, when you are watching horizontally this way, and you bring your eye down to an object at this level, there too you are talking about another angle. But that angle is called the angle of depression. So, what is the definition of angle of elevation? The angle of elevation is the angle between the horizontal line of sight. Line of sight is the technical word used in surveying for your eyes, what they see.
Hello. Hello.
Yes, you have to raise your hand. You didn't click on your hand. Anyway, is that easy? You can talk.
I didn't hear you again.
I thought you had a question to ask, or we can proceed.
No, yeah, you can proceed. I didn't hear you, so that was our calling.
Okay. Is it clear now?
Yes, please. Thank you.
All right. So when you talk of an angle of elevation, there should be the definition of the horizontal line of sight. This one should come first, number one, versus a line of sight up. Here too is technical. If your line of sight is not up, it's not elevation. You may be talking about depression. So note that as well. If it is elevation, the technical word of horizontal line of sight must appear, number one. And that's in combination with a line of sight up to an object, number two. If for some reason you go and write down here and you are trying to explain elevation, your definition is wrong. Then we come to angle of depression. An angle of depression is basically from the same line of sight for a horizontal line. This time you go down. So you try to deal with the line of sight down to the object. And that will describe the angle of depression.
Hello.
Yes.
Hello.
You are still struggling with your network. Yes. Can we proceed, Naki?
Is are you there? I can't hear you.
The network.
Hello.
Yes, I am here. Somebody can send a text to her. But
So we can hear you.
yes, I know it's a network. We're struggling with the network.
They can go out and rejoin.
Probably she's hearing it.
Hello.
We are suggesting that it's your network that is causing that. So at times you may have to go out of the platform and come back again.
If it is, well, we can't hear you. I don't know whether the others can
It's
hear you.
rather your network. Yes, we
It's rather
can
my
hear.
network.
Yes, please.
Oh, okay. All right. Thank you.
So Elizabeth, go out and come back, please.
Thank you.
You're welcome.
Sometimes when it's happening like that, when you go, you can't come back again. No.
All right. So that is a little about the angles. We are now moving on to bearings. And the reason why we have to come with angles first is that our definition of bearings and the types of bearings makes use of still angles in defining bearings. So what is our take home for the angles? Anytime two lines meet, so the next activity which you have to now start practicing, the other that I told you, you are going to need it for Sunday, but the practice must begin now. How do you measure angles with the protractor? That one I'm not going to teach it yet. You are going to have to work it out yourself. How do you measure angles with the protractor? Generally, this is how the protractor looks like. It's a semicircle. So you will know, or you will have to learn how to measure with protractor when it comes to angles. Like I said, a semicircle. From here, it's 0. It goes all the way and comes back to 180 on this other side. And there's another 0 there that goes all the way and comes to 180 on this side. So either way, you can move either clockwise or anti-clockwise. Drives the arc as you go along. So that is food for thought. That is for the take home. How we can use the protractor to measure angles. So we come to bearing. So I'll quickly introduce the subject, and then within about 5 minutes thereabout, we end. And we continue tomorrow. Same time, 7 to 9. Before Sunday. So when we say a bearing, what do we mean? A bearing may be specified in either of two systems. In fact, a bearing is the angle a line makes with a reference meridian. But there are two systems that take care of bearing. We have the whole circle bearing, and then we have the reduced bearing or the quadrantal bearing. What is the difference? When we move round this way, and we come back, you are moving in a circle. Do you all agree?
Yes, sir.
What is the total angle inside the circle when you move round, round, round? What is the total angle you select?
360.
360. Okay.
60 degrees.
Thank you. So that is clearly true, but there is something more. In that cyclic movement, you can have an angle which is more than 360. So what are the two systems about? We've admitted that when you go around a circle, you get 360. Later on, I'll indicate to you that when it comes to angles, you can go beyond 360. An angle can be, for instance, 400 degrees. An angle can be, for instance, 540 degrees. An angle, for instance, can be 900 degrees, as we saw in an earlier example. So what is the issue? When it is bearing, we don't go beyond 360. So we have seen generally that when you go around, it's 360. Now this 360, when I split it up into 4 equal parts, what am I going to get?
$90.
90.
Okay. What is another name for the 90-degree split? When you split this circle up, when you cut this circle into 4, the 90 that you get, what's the other name for it?
Right angle.
A quadrant.
Right angle.
Triangle.
It's called quadrant.
Right angle.
It's a right angle, yes, but it's also called a quadrant. Quadrant because there are two sides, two lines that are going to meet to define the right angle. All right. So when we talk of the whole circle bearing, the other we are saying is that we move clockwise and we complete our circle and keep moving, and that's the nature of the direction. We always move clockwise and in the circular path. It gives birth to what we call whole circle bearing. But there are rules there. In whole circle bearing, measurement is from 0 to 360 degrees. But you always move in a clockwise fashion. There was one bit I didn't add when I was talking about angles. So whenever we deal with the complete circle definition and we move clockwise, when I say clockwise, we all know how a wall clock moves. The wall clock. I'm not talking about the digital one. I'm talking about the old father's clock, the one that has the handle. And you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 12. That wall clock. When you watch the handle as they move clockwise. Do you agree?
Yes, sir.
Good. So whenever you consider that movement in a circle, always moving clockwise from your north, you have whole circle bearings. But the characteristic is that when you define bearings in whole circle, they are only numbers. There are no letters. But in the second system, where we call the reduced bearing or quadrantal bearing, we split this circle into 4 equal parts called a quadrant. And there are 4 quadrants we have to deal with. First quadrant with angular movement from 0 to 90. Second quadrant with angular movement from 0 to 90. Third quadrant with an angular movement from 0 to 90. And fourth quadrant with an angular movement from 0 to 90. However, in the second system here, the angular movement can be clockwise or anti-clockwise. In the first system here, all your movement is clockwise. Pick these details well. Whole circle bearing, we always reckon clockwise movement. Ima, your hand is up.
Yes, yes. It's like your last statement contradicts the whole circle bearing. I think that's what you explained earlier, that it has a anti-clockwise movement. If I may get you right, or if I'm not getting it,
I
then I
didn't
want.
say that.
Okay.
I didn't say that. So when you are in the whole circle, your movement is clockwise. And you read from 0 to 360 degrees. So note that whenever you're in the whole circle, you move clockwise. That's the only order in that one. From the north, called 0 or 360, you always turn clockwise. Ima, your hand is still up.
Oh, sorry, I'm clear. I'm clear now. Thank you.
All right. But when you're in the second system, some of the movements will be clockwise, other movements will be anti-clockwise. When we meet tomorrow, I will explain why in the quadrant concept, we have to move either clockwise or anti-clockwise. The reason simply being that in the quadrant concept, you cannot record movement more than 90 degrees because you are using quadrant. Secondly, in bearing definition, you reckon from the north. And this has a way it affects the reduced bearing notation or quadrantal bearing notation. So, what is a summary about? We've seen what an angle is. We've seen types of angles. We've seen under vertical angles, angle of elevation, angle of depression. So that is with the angles. Then we came to bearing. And we said bearing is the angle a line makes with the reference meridian. Meridian is north. Meridian is north. So tomorrow, when we come, I'll go back quickly to look at the knobs. How many types of knobs do we have in surveying? There are three. We have magnetic knob, we have geographical knob, and then we have grid knob. How do you find differences between these three knobs for tomorrow? So you have whole circle bearing, you have quadrantal bearing or reduced bearing. In the second one, everything's within a quadrant. So it means before you call out or write a particular bearing, you must know the quadrant you are in. To write it according to the language of that quadrant. Please, are there any questions before sign off? Jonathan, you have your hand up.
Yes, Doc, please, you made a document or material with us, but it hasn't been said yet.
Come again.
You made mention of sharing a material with us. I don't know if it's the one you are using to present or.
Jonathan, were you with me at the beginning of my lecture? Hello. Were you with me at the beginning of my lecture?
Yes, please.
Okay. Good. So whatever you had, you have to just suppose it with whatever that is happening. But my fundamental is still my fundamental. Do your notes. Any other question?
No question, Doc.
All right. So if there are no questions, then we sign off and we hope to meet tomorrow. Is that okay?
Okay, Doc.
Okay, Doc.
All right. So thank you all very much. And hopefully tomorrow at 7, we'll continue from where we have ended today. Have a good night.
Yeah,
We'll
thank
join
you.
back.
Thank
Same to you.
Bye.
Bye-bye.
Bye-bye.
Eddie,
Dog.
Please,
Hey.
the recording is still ongoing.
Enough for me, enough for me. Hey.
The recording is still ongoing. Please and please.
Hello, Mr. Sempa. Mr. Sempa.
Yes, dear.
Please, can I get your number?
Oh, yeah, yeah. I can get it.
Okay.
Let me put it in the chat box for you.
How can I see it? Will it display?
Yeah, if you go to the chat box, you see it. Where we put messages.
In fact, I don't know how to check that.
Have you seen it?
No, I don't know how to check it.
Madam,
Elizabeth, you
look
see
at
where
the
the
three
three
dot.
messages?
The
Uh-huh.
three dot. Click on it.
Let
Okay.
me, yeah.
It will pop up, and then you look at on top of the right,
Information.
at the left hand side on top in call
Yeah.
messages. Click on it. Have you seen that?
In call message. Oh,
Yeah, click on it.
Click that one.
okay. All right. Thank you.
Have you seen it now?
Yes, I'll send it.
Uh-huh.
Okay.
That's Empa.
59.
My
59,
boss.
last number.
Yeah,
It's
59
it's
last.
still
Okay, thank you.
I'm still not in the rep platform. Please, if you can add me there.
Oh, you are the rep for which center, please?
So you also.
Oh, okay. I think you should speak to. I am equally not on that platform. I'm the rep for Mauli.
Okay.
So you can speak to others who are platform.
And you can also
So,
do quadranter 10 on the vertical plane.
Okay.
what a terms.
It's getting interesting.
Well, it's not easy.
Nothing has happened yet, too.
It shall be well.
We hope so.
We
Mm.
hope so.
As for the world, yeah, BBF. BBF.
Last show mo no mo yɛ see. Last show no mo yɛ see. Ɛnti na mo de last days are dangerous no. Last days are dangerous.
Please, when are we meeting again? My network was
It is true.
connected me.
You say we'll be meeting
Oh,
tomorrow.
tomorrow.
Tomorrow at exactly 7 o'clock.
Okay. Okay. Thanks so much.
You're welcome.
All right.
Have a good day.
Good night to everyone.
All
Good
right,
night.
I'm signing off.
The day is over.
Bye
Bye bye.
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 Tomorrow we meet.
All right. Bye bye.